Hello again, welcome to the Academy, and this is a continuation of the video series on Cal 3 topics. This one's going to be about partial derivatives. So previously we talked about functions of multiple variables, and I just wanted to talk about how do we introduce calculus into this. And so the first thing we're going to talk about is how to take derivatives of functions. Now, if you remember derivatives of a single variable like f of x, you can take a derivative f prime of x by finding, say this is f of x, find the slope of a tangent line, and that will be the derivative. And there's a similar motivation for derivatives in multivariable calculus, but as we will see, it will be slightly different. So, a function of multiple variables, let's say for example a function of two variables, x and y, and let's use one that we did before, x squared plus y squared. And so if we graph it, the graph we talked about earlier looks something like this. So the parabola is rotated. So the question is, what is the tangent line at a point? Well, that's not really well defined. If I choose a point right here for a corresponding x and y value, this one has many tangent lines. In fact, you can actually find a tangent plane to it. That's not exactly what we want. But what we can do is we can take the derivative of a slice of this function, and that's what partial derivatives is. So what we do is we examine this point, and then we take a slice of the function in one of these directions, x or y. So basically, we take this point right here, for example, and we want to, this point corresponds to this x value. You just want to look at these x values, keeping y constant. And so what we create is sort of a plane that slices through this point, creates a little slice of the function. And so the tangent line that we're finding is the derivative of that slice at that point. There is a tangent line there. And that's how you do it. Similarly, you can do that in the y direction. That's called a partial derivative. So the partial derivative of a function can be denoted in a couple of ways. One way is similar to the Leibniz notation, is with a df and then divided by dx, but the d is curly in this situation. It's a partial differential. So this shows that it's a partial derivative with respect to x. So what we do when we see partial f and then partial x is, like we said, this is in the x direction, which means every other variable, in this case y, is assumed to be constant. So the partial derivative in this case, if we have y be a constant, we just get x squared plus some number, and then that would just be 2x. Similarly, we can do it with respect to y as well. If x is a constant, and the derivative of a constant is 0, the derivative of y squared is 2y. And that would correspond to taking a slice in the y direction at this point. Looking at the function that goes through it and finding the tangent line. Now another way of writing this is sometimes f with a little subscript x, or f with a little subscript y. So let's do another example now, let's say a more complicated function. So let's say we have f of x comma y equals x squared y minus 3xy cubed, for example. So now let's say we have this function. What we can do is we can take the partial derivatives so partial derivative with respect to x, we can treat y as a constant. So this is x squared times a number. So the derivative of that with respect to x, which would be 2x, and we just keep the constant there, minus, this is just something times x, and so we just drop the x, 3y cubed. Similarly, there's also fx, f sub y. Now we treat y as the variable of interest, and x is just a constant, so this is just a number times y, so the derivative would just be x squared, minus, so now we bring down the 3, becomes 9, x is just a constant, y squared. So now you may think, well, we can probably do more with this, and actually you can. Just like we have multiple derivatives in single variable, we also have multiple in multivariable. So we can take the second derivative, take the derivative again of this one, take the derivative with respect to x twice. Fx x is a similar notation to a single variable calculus. We have this, which equals, we'll take it with respect to x again, this is just 2y times x, this becomes 2y, and this is a constant, so minus 0, so it's 2y. Same thing, you can take fyy, so this is just a constant now, so 0, minus, well, if we bring that down, what does it become? 18 x, y, and so those are the second derivatives. But there's also a couple of other second derivatives. They're called the mixed second derivatives. It's what happens if I take first with x and then take the partial of that with respect to y. You can do derivative of x first, then y, x, y, is, if I take the derivative with respect to y, is 2x times y, so it should be 2x, minus, it becomes 9y squared. Or, alternatively, I can take the derivative of this, which is already with respect to y, now I take it with respect to x, f sub y sub x, so this becomes 2x minus, well, this is a constant times x, so that's just 9y squared. Now you may notice a strange situation that these two are the same thing. Even though we took one with x first, then y, and the other one was take it with respect to y first, then x. In fact, there's a theorem that says that if f is continuous and has second order partial derivatives, basically it's differentiable twice, then derivative of x first then y is equal to the second derivative where you take y first with x. So this is the equality of mixed second derivatives, or alternatively f sub xy equals f yx. And it does not seem very intuitive at first, but if you do some examples, you'll see that it does hold for all functions. So now let's do some examples, maybe a few more examples here, just to convince yourselves that in fact this equality does hold. So let's say we have something like f of xy equals x squared over y minus 2 to the x times y squared. And now the partial derivative with respect to x, well, what will that be? So with the x, this becomes 2x over y minus, which is a constant, y squared. Derivative 2 to the x, if you remember your rules, is 2 to the x times natural log of 2, log base e. Derivative with respect to y, well, this is going to be x squared times, well, if this is y to the negative 1, it would say bring down the negative and becomes y to the negative 2, so that would be negative x squared over y squared, minus 2 to the x y squared becomes 2y. And so now, just to show that these mixed second derivatives work, let's take the derivative with respect to y of this one. So this becomes 2x, so it becomes negative and y squared, minus, now we take respect to y, this is all a constant, there's 2y, 2 to the x, natural log of 2. Now if we take this one with respect to x, it becomes negative 2x over y squared, minus, well, the derivative, this is 2y, and 2 to the x becomes 2 to the x log 2. And once again, they are the same. And let's just do one more example. This can be done with more than just two variables. So let's just do one more example here. F of x, y, and z. Let's say it's x cubed y z squared minus xy over z plus z to the fourth. So now we can find partial derivative with x. It'll just be 3x squared, and the rest are constants, y z squared, minus, well, this is just constant times x. This is a constant, so it becomes 0. Partial derivative with respect to y is, well, this is just constant times y, so it's x cubed z squared, minus, again, just a constant, x over z, and it's a constant, so it's 0. And then partial derivative with respect to z becomes 2 x cubed y z. So this will be minus, but this will be a negative, so it will be a plus xy is a constant divided by z squared, and then plus 4z cubed. You can see that you can do it with any number of variables, and taking the partial derivative, simply you ignore every other variable except for the variable that you are taking the derivative of and treat it as a constant. And that's basically all there is to partial derivatives. And I'll see you in the next video.